let's briefly review what these conversion formulas between polar coordinates and rectangular coordinates. Well, so number one thing to recall, instead of just looking at these formulas, and so I think it's important to look at where they come, where they are coming from. So, for example, if we have this Cartesian plane here, and we have a point, any random point in the plane, on the plane, and well, we can define this point as well, this point is x comma y, all right, and that point can be defined as being some units away from the origin. So there's a length between the origin and that point, which we usually call it r, like the radius, if you will. The thing here is that the distance to go, when we go from the origin to this point x, y in the plane, we're moving x units in the horizontal direction and y units in the vertical direction. This forms a right triangle, and this right triangle has an angle, a related angle, and in this case, if we redefine this y and x in terms of trigonometric functions, well, what do we have? This is the vertical component. This is basically like opposite over hypotenuse. That's going to be our r sine theta, and r cosine of theta. All right, and this point x comma y is redefined as radius time and angle, not times, radius and angle. So when it comes to polar coordinates, so as opposed to rectangular coordinates, what we usually do is walk a number of units in the x direction and some units in the y direction. So that's what we call it, the rectangular system, or besides the Cartesian system. And well, in this case, when it comes to the polar system, we no longer go x and y. We actually stare at in the positive x direction, and the number of units that we walk, in this case, it's going to be defining the radius. And instead of walking up, we're going to move our camera, if you will, at an angle, and so we will be defining radius and angle as opposed to length and width in the Cartesian plane. So these are the formulas that we use to convert between the two systems, to go back and forth between the two systems, to find the angle and to find the radius and all that, etc. So let's grab the polar function r equals to 5 and convert to rectangular form. Well, so when we read this statement, r equals to 5, what's the first thing that comes to our mind? It's a circle, right? Because that r is usually used to denote a circle, and to denote the radius, and the only shape that we relate with a radius is indeed a circle, right? So it's a circle of radius 5. So that's, or in other words, we're looking for all the points that are 5 units away from the origin. And well, by the definition of the circle, which is all the points that are equidistant from a fixed point called the center. In this case, it's indeed the circle. And then we need to convert this equation back to rectangular form. So, well, what are we going to do in this case? Notice one of these relations that we use to convert between polar and Cartesian. So we're going to replace that here. Whoops, not that one. And we're going to get square root of x squared plus y squared equals to 5. And well, that's not really the correct form, so all we have to do is square both sides to get rid of the radical. And well, indeed, if we look at this equation in Cartesian coordinate, or in the xy world, x squared plus y squared equals 25. That's indeed the equation of a circle with a radius equal to 5. All right. For the next exercise, example 2, they're asking us to express this surface in 3 dimensions in polar form. Right? So what are we going to do here? So we are going to replace this x and y into r, theta. Well, let's see what can we do about it. So notice this x squared plus this x squared and y squared. So somehow will be related to one of the expressions here. However, these two x squared and y squared have a negative sign in front. So what we're going to do in this case is factor that negative and check this out. X squared, whoops, it's actually going to be related with this and simply, oh come on, that's square root of 16 minus x squared plus y squared. Oh, wait a minute, no, r squared. All right? And that's a function that no longer depends on x and y, but it's actually a function described in the world of r theta. Well, in this case, this one doesn't include any angles at all. A very typical region. So now let's talk about regions. You know how we integrated in the previous section, we integrated over rectangular regions, for the simplest cases. So we're going to talk about rectangular regions in polar coordinates. So, and we're going to be describing this by, well, that polar rectangle, which is not going to have the shape of a rectangle. Well, you'll see why. And it's described between r, for r between 4 and 9, and the angle will vary between pi and 2 pi. So number one, what's this r between 4 and 9? So in this case, the way we want to understand this one is by, well, let's draw 2 circles. This describes everything inside of the circle of radius 9 and greater than the radius of 4. So that's the smaller circle, the one, well, that's not very centric, and so that's the smaller circle, the one with a radius of 4, and that's the one with a radius of 9. However, we just want to sketch the region that goes between pi and 2 pi, so not the whole region in this case. So to better describe this region, we're just going to shade the part that varies only between pi and 2 pi. All right, pi 2 pi. All right. So we're going to look at this region later when we set up some of the integrals that will be redefined in terms of polar functions. Now, how do we change those integrals in particular from the world of xy to the world of r theta? Well, in the world of xy, so we just looked at the change in the x direction and the change in the y direction. That dA meant dy dx or dx dy depending on the direction that we chose, whether this is vertically simple or horizontally simple. Now, this dA in the world of polar, it's going to be r dr d theta. Well, where is this coming from anyway? So let's consider this circle. All right, let's consider this circle right here. And I'm going to take only a portion of the circle, one sector. And, well, so in a similar way that we found the area under the curve for a function f of x by chopping the region into 4 rectangles, 5 rectangles, infinitely many rectangles. So what we're doing essentially here is to get a portion of a disk, so not even the whole disk, it's actually a sector of a disk. Now, recall that these points in the polar system are depending on some radius r, right? So from the origin to the outermost point in the circle, that's r. However, this tiny piece of the sector, it's going to be some, let's call it radius, or radius 2. Okay, let's call it, for example, radius 2. And let's call this a radius 1, right? So essentially, since we're finding that length of that radius, essentially we can call it an increment, if you will. So let's call this a dr, all right? That portion that will be the dr. Now, so let's say that we want to find that area of that sector. So let's go back, let's grab this piece of sector and actually turn it a perfect rectangle, all right? So, number one, this length, isn't it the arc length? And that arc length, let's call it S. Isn't that r theta? All right? Well, in this case, so we are going to have this, where is that on my notes? So, well, in this case, that's just going to be some d theta, because we're looking at an increment between some, let's call it this time a theta 1, and let's call it a theta 2. Theta 2 minus theta 1 is just going to be some difference, right? Some d theta. And well, if we find this area, oh, that's fine. This r d theta, dr, so this dA will become r dr d theta, which is the one that we have in the conversion, all right? So that's where that extra r is coming from. And well, so in this case, what do we have? R being a plane region consisting of all the points where x is r cos theta, y is r sine theta, satisfying the conditions. Well, G2 is greater than G1, and the angles between alpha and beta, actually, they vary between 0 and 2 pi, as usual from back in calculus 2, all right? And of course, we need to make sure that G1 and G2 are continuous along that interval of angles, all right? So let's look at some examples how we go about integrating this. Okay, so let's look at this integral. So evaluate the double integral of 3x plus 4y squared dA, where r is the region bounded by the circles x squared plus y squared equals to 1. And x squared plus y squared equals to 4. All right. So number one, if we wanted to instead evaluate this integral in rectangular coordinates instead of evaluating in polar coordinates, well, then we would have an issue here, because double integral 3x plus 4y squared, well, no, this one is not going to be troublesome. This one is going to work fine anyway. So and for the further examples will show us the advantage of converting our systems into the polar system to easily solve the problem. So let's sketch. So let's sketch these two circles. So one of the circles is the circle of radius 1, and that circle has a radius equals to 2. And so those are the two circles. All right, so in this case, let's convert this integral into an integral that it's changed in the world of radius and angle, no longer an integral in the world of xy. So let's write down the double integral first. And well, using the conversion formula, so to avoid flipping pages or scrolling up and down, let me write them down again. X equals to r cos theta and y equals r sine theta. So those are the two conversion formulas that we're going to use to rewrite this integral in terms of r and theta. In other words, we're going to do this. Plug in r cos theta whenever we see the letter x, and plug in r sin theta whenever we see the letter y. Now, so that's going to be 3r cos theta plus 4 times r sin theta quantity squared. Be careful here when squaring this. Now, the dA will become r dr d theta. Now, we need to figure out the limits of integration. So we're no longer in the world of x and y. We are looking at the radius and the angle. So the innermost integral, it's an integral that depends on r. So we're going to look at the radius. So in this case, we're looking at the area. Well, it's not the area, it's going to be the volume anyway. So the limit for the radius, so we have the radius equals to 1 and the radius equals to 2. However, in this case, since they're not telling us, they're not bounding the region this time to only pi to pi in this case. Since they're not giving us any bounds, like the lower half or the upper half in the problem, we're assuming that we are evaluating this integral over the entire region. And in this case, this entire region goes from 0, goes around the circle to 2 pi. So if the wording were, we're only integrating over the lower part of these circles, it would have been between pi and 2 pi. All right. Well, so let's evaluate this integral. So number one, let's simplify. So that's the double integral from 0 to 2 pi. Let's simplify the integrand. So this will be 3r cosine theta plus 4r squared sine squared. Be careful because this square will affect both the r and the sine. R dr d theta. And then from here we need to distribute this r over here and over there. So this will be the integral from 0 to 2 pi, and that's 3r squared cosine theta plus 4r cubed sine squared theta. I'm going to need some space for the differentials. And that no longer r, that's just dr d theta. And well, in this case, all we have to integrate, so we're going to do some partial integration. But in this case, the first integral is going to go with respect r. So in the first term, that cosine theta will be constant, and in the second term, that sine squared will be held constant as well. So really, the integral of 3r squared, that's simply, isn't that an r cubed? Cosine theta plus r to the 4th sine squared theta. And that gets evaluated between 1 and 4. And again, we are only integrating, yes, 2. Yes, thank you. I was looking at the equation instead. So from 0 to 2, but we're only plugging this in our r's. All right. So that's going to be the integral from 0 to 2 pi. So this will be, so 2 cubed, which is 8 cosine theta, plus r to the 4 or 2 to the 4, which is 16. So that's the upper limit minus lower limit. So that's 1 cubed, and 1 to the 4, that's still just 1. So that's going to be minus cosine theta plus sine squared theta, d theta. So we're done with, well, I actually forgot the d theta here. All right. So let's simplify the integrand right here. So let's combine like terms, x cosine minus a cosine. That's going to give us a 7 cosine, and 16 sine squared minus 1 sine squared. That's going to be a 15 sine squared. So let's write that down. So that's the integral from 0 to 2 pi. And that's a 7 cosine and minus 15 sine squared theta d theta. So that reduces for now to an integral that depends on one variable. It's a single integral. It's no longer a double integral. So let's see. Let's integrate each term. Well, the integral of cosine, that's going to be sine. But how about integrating sine squared? Can we integrate sine squared just right away? No, right? We'll have to use a trigonometric identity in this case. Let me write that down below. So,
Plus 15 sine squared, right?
is that, yes, please, yeah, that's what I meant. Plus 15, thank you. So we will have to use 1/2, in this case, minus cosine to theta. So we'll have to replace with that identity, and that's equal integral from 0 to 2 pi. That's 7 cosine theta plus 15 times 1/2 1 minus cosine to theta d theta. So this will be, distributing this will be the integral from 0 to 2 pi. That's a 7 cosine and 15. Oh, come on. 15 halves and minus 15 halves cosine to theta. And well, after we may go about the integration. Well, we can integrate cosine, that's going to be sine. We can integrate 15 halves, that's going to be 15 halves theta. And we can integrate 15 halves cosine of 2 theta, that's going to be 15 halves times the integral of cosine 2 theta, which is sine 2 theta, but times a factor of a half, which will be, okay, that's 7 sine theta plus 15 halves theta minus 15 halves, and that's a sine 2 theta. But when we integrate this sine to theta, we should multiply by 1/2 and evaluate from 0 to 2 pi. So that'll become, number 1, 7 sine theta minus 15 theta over 2 minus 15 over 4 sine 2 theta from 0 to 2 pi. Well, what's going to happen here? Let's evaluate upper limit minus lower limit. So the upper limit, so we have 7 sine of 2 pi minus 15 times, or 15 halves times 2 pi minus 15 fourths sine 2 times 2 pi. Now that's the upper limit. However, for the lower limit, which is 0, okay, what's sine of 0?
0.
What's, well, 0, that's going to get zeroed out. And what's sine of 2 times 0, which is 0? Another 0. Can we just write big 0 instead? Well, still, this is 0. 0 because sine of 4 pi is 0. Sine of 2 pi is also 0. And we will be left, that's actually positive. I don't know where I got the negative from. And this will be, cancel these two, that's 15 pi. Alright. So that's our first example on how we evaluate an integral using this polar coordinate. So I think it's a good time to take a break.